Welcome to this lecture. This is the second lecture of week 7. In the first lecture, we have finally completed the proof of all the equivalent statements that we had stated for weak convergence of probability measures. What we have essentially talked about in that set of equivalences were that it can be defined through certain type of convergences for the corresponding distribution functions, but we can also see the similar conditions, but in terms of integrations involving certain nice class of functions and also involving certain measures of open sets, closed sets and other mu continuity type sets, where mu is the limit probability measure. We have also expressed another equivalent condition through the Levy's continuity theorem through the corresponding characteristic functions. This was in terms of the pointwise convergence of the corresponding characteristic functions. So, this description of all these equivalences now gives us a good background to see further properties of weak convergence. However, we recall that in the previous lecture we have actually stated one result called the Skorokhod representation theorem, which we have used in our proof without proving the Skorokhod representation theorem. So, in this lecture what we are going to do is to first talk about the proof of the Skorokhod representation theorem, and we are also going to see some other nice sufficient conditions which will be useful in checking the weak convergence for probability measures as well as associated random variables. So, without further delay, let us continue the discussion using the lecture notes. Okay. So, we start our discussion today by looking at the proof of the Skorokhod representation theorem. So, this was theorem number 1 as stated in the previous lecture. Alright. So, let us start. So, we are given a sequence mu n of probability measures on R, and we are given that that sequence converges weakly to another probability measure mu. Now, what we would like to do as part of the theorem to construct certain sequences of random variables with these probability measures as their law and showing pointwise convergences. So, let us see, and for that what we will also require is that this random variable are supposed to be defined on the same probability space. Okay. So, let us see. So, now what we are doing is that we are going back to our standard choice, which is this omega being the interval 0 to 1. So, here we are taking it to be the open interval 0 to 1. Now, on top of omega we have to specify the corresponding sigma field and a probability measure. So, here what we are doing is that we are taking the Borel sigma field on this space along with the corresponding probability measure being the restriction of the Lebesgue measure to this collection of subsets. So, here we have a probability space. Now, since we are given this sequence of probability measures, we can choose to look at the corresponding distribution functions. So, let us say f n denotes the distribution function corresponding to mu n and f denotes the distribution function corresponding to mu. Now, what we do is that on this specific probability space we construct certain explicit random variables. So, here there is this sequence we are going to construct and another random variable y on this specific probability space. Remember, omega for us is the open interval 0 to 1. Now, here what we do is that we choose small omegas coming from this open interval 0 to 1 and define y n's this way, that first given that number omega for the positive integer n, what we do is that we look at this inequality and we consider all such real numbers small x for which this inequality is satisfied. So, this forms a set, and what we do is that we look at the infimum of this set. Remember, for every fixed value of n, the limit of these distribution functions as x goes to minus infinity, that is 0. So, this is a property of the distribution function f n. Now, therefore, if I look at this lower bound given by omega, then there will be some x which does not satisfy. So, what we are essentially saying is that this set of points that we are considering, the set of small x's, that is actually lower bounded, and therefore, there is a infimum, and that infimum is what we are calling as y n of omega. And similarly, we define the function or the random variable y in this way, that we look at first the distribution function f, and corresponding to this specified value small omega, what we do is that we ask for this inequality to be satisfied. So, that will give us a range of small x, and we want the infimum of all such small x, and that is what we are going to define as y of omega. So, here what we note is that we have explicitly defined these y n's and y. Now, what we observe are certain nice properties which follow immediately from the definition that we have just considered. So, here what you can see is that this inequality, that is part of the definition, this now holds if and only if y n of omega is less or equal to x. This can be checked, and that is left to you for an exercise. Please check this. Now, again a similar statement is again true when you are considering the distribution function capital F. Again, if you consider this inequality, then this inequality is true if and only if y of omega is less or equal to x. Now, what we are going to do is to look at these equivalences and observe certain nice things. So, the first observation that we make is that we are going to determine the distribution function of y n. So, here we note that we want to look at the probability of the event that the random variable y n takes the value less or equal to small x. Now, again let us write it explicitly. What we want is the set of points small omega such that the y n of omega, these values are less equal to x. So, this gives us an event, and we want the probability of that. Now, here you note by the equivalence that we have just discussed, we can rewrite using this condition now. This is just an equivalent condition which was stated as an exercise above. Now, once you have that, remember here we are taking omega from the open interval 0 1, and the probability measure p is nothing but the restriction of the Lebesgue measure. Therefore, this should be Lebesgue measure of this interval 0 to f n of x closed. All right. So, this is just following from the observation that omega has to be first of all falling inside the set 0 to 1, and then what we observe is that omega is less or equal to f n of x. So, therefore, omega is in the left open right closed interval given by this, and we want the probability of that, which is nothing but the Lebesgue measure. So, that Lebesgue measure of this left open right closed interval is f n of x exactly. So, therefore, what we have now identified is that for all arbitrary values of x on the real line, we have the probability of y n less equals to x. So, that is essentially identifying the distribution function of y n, and therefore, what we end up having is that this is exactly the function f n. So, therefore, the random variables that we have constructed for each positive integer n, which are these y n's, have the distribution function f n. What is the consequence of that is this, that the distribution function of y n is f n, and consequently, the law must be given by the corresponding probability measure mu n. So, this simply follows from the understanding that there is a correspondence between the probability measures mu n and the corresponding distribution functions f n. So, if the distribution function of y n is f n, then the law of y n must be mu n. Similarly, we can look at the distribution function of the other random variable y, and here what we will again have that the distribution function is exactly capital F, and hence the law of the random variable y must be mu. Now, once we have this observation, it is now time to look at their corresponding convergences, and as part of the statement of the theorem, we actually want to claim pointwise convergences. So, let us see. So, we want to claim that this actually is true for all omega. Now, let us see if this is true or not. Now, given epsilon positive, we first what we are going to do is to choose a point small x, which is a continuity point of the distribution function capital F. So, here note that the distribution function can have at most countably many points of discontinuity, and therefore, outside that if you choose a point, so that is a continuity point. So, and such points are dense on the real line. So, given any such epsilon positive, we can always find such a continuity point in this range of values. So, what we are looking at on the real line, we are looking at the value first of all y of small omega, and we are also looking at y of small omega minus epsilon. So, inside this open interval I must find a point of continuity small x. So, that is all is following from the density property of this set of continuity points of the distribution function of capital F. All right. So, now choose that continuity point. Note here that the measure of this singleton is exactly 0. So, this is again restating the continuity behavior of the corresponding distribution function, which is capital F. Now, look at this inequality that x is actually strictly smaller than y omega, that is by our choice, and hence by our earlier exercise we can again conclude that then f of x must be strictly smaller than small omega. Now, note that we have actually taken that limit of these fn's are going to f x, right. So, for all the continuity points and therefore, for the point small x that we have considered. Since we are having this, what we have is that there must exist a natural number which we denote by capital N 1, such that the terms f n must be smaller than omega after that stage, this is N 1. So, this will be corrected in the lecture notes. So, what we are saying is that as f of x is less than omega and f n of x, that sequence of values converges to f of x. So, therefore, after a certain stage the terms in the sequence will also be smaller than small omega. Once you have that, then we immediately conclude from this inequality that we must have now on the left hand side we already have y of omega minus epsilon is strictly less than x. So, that part is already there, but now we observe that again by the equivalences that we have considered earlier, what we are having is that small x must be strictly less than y n of omega, and this is happening when small n is greater or equal to this level capital N 1. But now, here what we have actually done is that given this arbitrary choice of small epsilon, we are constructing this number capital N 1, and therefore, using this arbitrariness of the epsilon, what we conclude is that the liminf of y n. So, a priori I do not know whether this limit exists, but liminf certainly exists. This must be greater than y of omega. This simply follows from these inequalities that after this stage capital N 1, all the values y n of omega are actually strictly greater than y omega minus epsilon, and using the arbitrariness of epsilon we are ending up with this relation that liminf of y n of omega must be greater or equal to y of omega. Now, the standard step would be to look at the lim sup of this sequence. So, let us see. So, to look at such quantities, what we do is that we first choose any point omega prime greater than our small omega. Now, again choose another arbitrary epsilon positive, then again we can choose a continuity point of the distribution function capital F. We call this point as small y, but with this property that small y now falls inside the interval y of omega prime to y of omega prime plus epsilon. So, we are looking at that open interval now, that we now want a small y here, which should be a continuity point of the distribution function capital F. This again follows from the fact that the continuity points of the distribution function capital F are dense in the real line. So, therefore, we can always choose such a number small y, but then we observe this set of inequalities that since omega is less than omega prime, we must actually have that omega prime also is less or equal to f of y. So, this just follows from our earlier inequality through which we have chosen our point small y. So, therefore, by observing this fact, again by the convergence of f n of y to f of y, what we conclude is that there must exist a natural number n 2 now, such that for all natural number small n greater or equals to n 2, we must have this inequality being satisfied. All right. So, this is again another type of an observation that we have used in the lim type of arguments, but we are just repeating a similar argument through this choice of omega prime. So, once you have this set of inequalities are true for all small n exceeding capital N 2, then again using the arbitrariness of our epsilon that we are working with, what we conclude is that lim sup of y n of omega must be less than or equal to y of omega prime, but this is true for all omega prime greater than omega. Remember, we have started our argument involving lim sup by looking at the choices omega prime greater than omega and epsilon greater than 0, and we have made our argument. So, therefore, the final conclusion is true for all omega prime, and by removing our arbitrary epsilon we end up with this inequality. But now, what we do is that we would like to approximate the points omega from the right by omega prime, and we will look at the corresponding values of the random variable y. So, we are now looking at the approximation of y omega through the y omega primes. Now, here if it so happens that y is continuous at the point small omega, then just by using the right continuity, using the approximations from the right through these omega primes, we will simply have this inequality being true. Now, what we will have therefore, if y is continuous at omega, then combining the inequality for lim inf together with this double star inequality, we will conclude that the limit exists and it equals y of omega. Remember, at these continuity points what is happening is that we are having that y of omega is greater or equals to lim sup of this quantity is y n of omega, but lim sup is always greater or equals to lim inf of y n of omega, and then that we have already shown to be greater than y of omega. So, therefore, we must have equalities. So, that is what is happening if y turns out to be continuous at this point small omega. Now, original goal was showing that this limit is true for all points small omega on our domain. Now, here what we have managed to show was that the limit holds only at the continuity points of y. So, what we are actually going to do is to update our existing random variables in order to get this limit also at points of discontinuity of this y. So, to see this, what we observe first is that by definition y must be non-decreasing. Now, here as soon as y is non-decreasing, it has either a finite number or a countable infinite number of discontinuities. So, the behavior is similar to what you see for a distribution function, but since we have actually explicitly constructed these random variables out of these properties of the distribution function, these kind of properties also continue to go through for the function y. So, therefore, y has either a finite number or a countable infinite number of discontinuities. Now, what we do is that we denote this set of discontinuities by d of y. So, here d of y is either finite or countably infinite, but remember we are working with the restriction of the Lebesgue measure in this probability space setting, and therefore, this at most countable set d y that we are working with must have measure 0 under the Lebesgue measure. So, let us observe this fact that probability of d y is actually 0, but now what we observe is that on those points where the discontinuity occurs, we will be able to revisit or redefine the random variables that we consider. So, now what we see is that we are going to update our sequences to y n tilde and the other random variable from y to y tilde. in this way that for all points small omega in our domain, what we do is that we define this y n tilde this way, that if our omega is in the complement of the discontinuities of y, then we continue with the actual values of the sequence that we already know about, otherwise we will set it to 0. Now, here you note that on these points on the complement of dy, we already have shown the pointwise convergence. We are just redefining the random variables in question only at the points of discontinuity and obtaining new random variables. Similarly, we are going to look at y tilde defined in an analogous fashion, that on the complement of the points of discontinuity of y, we will continue to keep the original values, otherwise we will set it to be 0. Now, here you note what is happening is that on the points of continuity, basically the complement of dy, we are already having the pointwise convergence, but now we are enforcing the pointwise convergence on the discontinuity points by setting everything to 0. So, therefore, immediately we have these several observations now. Since y and y tilde only differ on certain countable number of points and under our setting this has measured 0, then the law of y and y tilde must be same. Similarly, the law of y n tilde and y n must be the same, because we have only changed the values at countably many points. So, therefore, as a consequence of that, we have this set of observations that the distribution function of y n tilde must be f n with the law mu n, and the distribution function of y tilde must be f together with the law mu. And finally, by our construction y n tildes actually converge to y tilde, and this happens now for all points in our domain. So, remember, our original claim that we made was for limit of y n of omega equal to y of omega, that was for all points. So, we were unable to prove this claim, but what we have obtained is that we are able to redefine the existing y n's and y to this y n tilde and y tilde, such that now the pointwise convergence is true, and we are proving therefore our claim for the new sequence y n tildes, and they converge pointwise to the y tilde. So, this completes the construction that was part of the proof of Skorokhor's representation theorem. All right. So, with this understanding, our proof of all the equivalences that we have discussed earlier are now complete. So, now what we are going to do is to focus on certain specific sufficient conditions which imply the weak convergence, and this will be useful in practice, because we are going to state certain nice classes of random variables, and these will be slightly easier to verify in practice. So, let us see. So, the first thing that we are going to consider are absolutely continuous random variables, meaning their distribution functions are given in terms of certain probability density functions. We are now going to write it as PDFs. So, the conditions now that we are going to consider will be in terms of the corresponding PDFs. So, here we start with this sequence x n of absolutely continuous random variables with the corresponding probability density functions f n. Now, if it so happens that these probability density functions, the versions of them converge to another version of the PDF of capital X, that it holds for all x almost every Lebesgue measure sense, then what we are having is that x n must converge weakly to x. So, the idea is that you are having this sequence of absolutely continuous random variables, such that you also have another limit random variable being absolutely continuous, and the pointwise limit of the corresponding probability density functions hold almost everywhere with respect to the Lebesgue measure sense. Then the weak convergence holds. So, how do we see this? So, again we are going to use one of the equivalent conditions that we have discussed earlier. So, we start off with a bounded and continuous function. Here as soon as the function is bounded and continuous, we can look at the supremum of the function mod g. Then that quantity is exactly the essential supremum. All right. So, now what we consider are these specific functions which maps any real number small x to this number, that g of x plus the L infinity norm of g, and the second function is L infinity norm of g minus g of x. Note that always we are having g of x falling between these numbers, that g of x falls between minus L infinity norm of g and upper bounded by the L infinity norm of g, and therefore, the functions we are considering now must be non-negative. Now, for this non-negative continuous functions, what we also observe is that by the pointwise convergence that we are given, we are also having that this multiplied by f n as n goes to infinity goes to this. Similarly, the other functions that we are now considering, again these quantities do not depend on n. So, if you multiply by f n as n goes to infinity, they go to this, and this pointwise convergences hold for Lebesgue almost every x. Now, we can appeal to Fatou's lemma and get certain nice statements. What we observe is that if we start off with the expected value of g of x, remember g is bounded and continuous. So, g of x is a bounded random variable. So, expectation exists. So, all we are considering now are these expectation plus this constant, but we can treat it as the expectation through this, where we are just integrating with respect to the PDF of the random variable capital X. So, this is now an integration involving the probability density function of capital X. Now, here you note that the integrand here is a pointwise limit, and here is where we are appealing to the Fatou's lemma. So, therefore, we are going to have less equal to lim inf the integral of these quantities, where the integration has now been replaced with respect to the probability density functions f n. All right. Now, again observe that these inner quantities can be rewritten in terms of this expression, that this is now expected value of g of x n plus this constant g infinity. So, again we can do a similar inequality involving the other functions, and we will end up with this inequality. So, if you combine these inequality, then what we are saying is that for all bounded and continuous functions g from the real line to real line, we are having this set of inequalities, and since lim inf is by definition less or equal to lim sup, we must have equalities, and moreover the limit must exist and it must be expected g of x. However, note that g is chosen to be bounded and continuous, and here we have managed to show that expected value of g of x n converges to expected value of g of x. Here you recall that this is an equivalent condition for convergence in the sense of weak convergence. So, therefore, the corresponding random variables x n's must converge weakly to x. So, that is what this sufficient condition tells us. So, we see a quick application of this result. So, here we recall first that we have earlier discussed the weak convergence of Gaussian random variables. So, this was discussed earlier in the previous week in remark 11. Please go back and check. So, here what we are considering are a sequence of Gaussian random variables with mean mu n and variance sigma n squared. So, we go with sigma n squared positive. Now, if it so happens that the limit of mu n is mu and the limit of sigma n squared is sigma squared, which is positive. So, that is part of our hypothesis. Then what we can consider the limit random variable x following the Gaussian distribution. So, this is convergence in the sense of weak convergence, and this was discussed earlier in remark 11. Now, what we are going to do is to consider the corresponding pointwise convergence of the probability density functions that we have just discussed, and we are going to again prove the same fact that x n's converge weakly to x through the pointwise convergence of the corresponding PDFs. So, here for all points x in the real line, look at the limit of the pointwise values of the corresponding PDFs. So, here we explicitly write down the expression. So, now we are given that mu n's converge to mu and sigma n squared converge to sigma squared as n goes to infinity. So, therefore, we immediately will have that the limit function is given this way, but that is exactly the probability density function of capital X evaluated at small x, and therefore, since this is true for all x, we immediately claim that x n's must converge to x in the sense of distribution or in the sense of weak convergence. Now, here what we actually have used in our earlier proof is the expression for the expectation like this, that it can be expressed in terms of an integration with respect to the probability density function. Now, you can ask, this was for the case of absolutely continuous random variables. What happens if we consider discrete random variables? Again, if you are working with a discrete random variable x with a support set S x and a probability mass function f x, then the corresponding expectation exists because G is assumed to be bounded and continuous. So, then you can get it through this kind of series. So, here as long as the series converges absolutely, you will get the expectation given like this. Now, again if you argue similar to the calculations involving the probability density functions, the pointwise convergence of it, we are actually going to get a similar kind of statements when you consider discrete random variables. Again, we do not want to repeat the type of arguments. So, we are skipping the proof, but it goes through similar type of arguments. So, for simplicity we state the theorem in this way, that we are considering these random variables x and this sequence of random variables x 1, x 2 and so on. These are discrete random variables, and suppose for simplicity that all of these are supported on non-negative integers, and suppose the corresponding PMFs are given this way. Now, the statement says that you can actually show that x n converges weakly to x if and only if the pointwise convergence of the corresponding probability mass functions holds at all points of the support. So, this you can try to check again by using similar type of arguments, and we now see immediate application of this result for the case of discrete random variables. So, this is an important result that is quite useful in practice. So, this result is Poisson approximation to binomial distribution. So, the idea is this, that we are going to consider a sequence of binomial random variables, and under certain conditions we are going to say that there is a convergence to Poisson random variables. Now, here the convergence that we are using is the sense of weak convergence. So, therefore, whenever we want something involving binomial distributions for large enough n, we can possibly approximate it using the limit distribution, which is the Poisson distribution. So, that is why this result will be called Poisson approximation to binomial distribution. Let us see. So, here what we will consider is that the support set is considered on 0, 1, 2 and so on. Alright. So, that is the support set of the Poisson random variable, but again the binomial random variable with number n here, that will be supported on 0 to n. So, therefore, this can also be thought of as support contained inside here. So, once we have that, what we are going to look at are the pointwise convergence of the corresponding probability mass functions. So, let us see, we are considering a sequence of random variables which are following binomial distribution with parameters n and p n, such that n times p n as n goes to infinity converges to lambda. Then the claim says that x n must converge weakly to x, where x follows Poisson lambda. So, let us see here what we are going to do as part of our earlier result. We just have to verify the pointwise limit of the corresponding probability mass functions. So, therefore, for every value of non-negative integer j, we are going to look at the probability that x n equal to j, what happens to that probability as n goes to infinity. So, let us write down the expression for the probability. So, remember here that j is kept fixed and n goes to infinity. So, therefore, after a few values of n, we must have n is greater or equal to j. So, therefore, all such values of n, immediately we will be able to write down the expression for the corresponding probability mass function as this expression, and we want a limit of this expression as n goes to infinity. Now, we manipulate this expression in this way that we first break this binomial coefficient. So, we will have 1 by j factorial outside and the remaining terms are like this. Now, what we do is that we divide and multiply by n to the power j. So, here what is happening is that the division is kept together with this expression and the multiplication is kept together with this expression. So, now here we observe first that this first expression, the first ratio as n goes to infinity for fixed values of j goes to 1. Also n times p n by our assumption goes to lambda. So, therefore, combining everything we will end up with this limit as n goes to infinity, but this is exactly the probability that a partial random variable x with parameter lambda takes the value j. So, therefore, we have verified the pointwise convergence of the corresponding probability mass functions and therefore, our statement now follow from our previous theorem. So, we see a immediate application of this result. So, suppose we take a binomial random variable y. So, suppose it has this parameter 1000 and probability of success being 0.003. So, then what we can consider is the approximation by Poisson distribution. So, here if we are interested in the probability of y equal to 4, this will be given by this complicated looking expression which is hard to compute. However, if we consider the corresponding approximation by the Poisson distributions, what is the lambda we need to use? So, the lambda should be considered with 1000 times this number which is just 3. So, if we consider the probability of y equal to 4 approximated by probability z equal to 4, where z follows Poisson with parameter 3, then we will immediately have this approximation for this earlier probability, which is quite easy to compute compared to the earlier expression. All right. So, we finish with certain important remarks. So, earlier we have seen 3 other modes of convergence: convergence in LP, convergence almost surely and convergence in probability. All of these were in the setting where we are considering the random variables to be defined on the same probability space. The fourth type that we are considering is allowing us to look at random variables on different probability spaces. However, what we have earlier pointed out was that convergence in LP and convergence in probability are metrizable, whereas convergence almost surely is not. Here what we comment is that weak convergence or the convergence in distribution actually is metrizable. So, we do not go into complete details, but we give you a quick overview of this idea. So, let us see. What we are saying is that let us look at the collection of all probability measures on the real line together with the Borel sigma field denoted by script p. Here we can actually talk about some kind of a distance function on this collection of probability measures given like this, that for every epsilon positive and every Borel set, we first consider kind of a neighborhood of the set capital A given like this, that we want all points in the real line such that there is a point in the original set which is close to it by the epsilon distance. So, we are now considering all such points which are quite close to the set A. So, the idea will be that if your set looks like this, we are just enlarging it on both sides. So, that is the epsilon distance that we are considering. So, now if you look at these sets A epsilon, using these sets what we will now consider is this specific distance function on P. What we do is that given any two probability measures mu and nu, we look at these inequalities in the sense that we first look at measure of A getting dominated by measure of A epsilon, but using the second measure plus epsilon. This should hold for all Borel sets and vice versa, meaning the new measure of A should be dominated by the mu measure of A epsilon plus epsilon. Remember that if we take epsilon to be 1, these inequalities are automatically satisfied, because the left hand side expressions are dominated by 1. The type of points that we are considering in this set includes 1. So, therefore, if we consider the infimum is less or equal to 1. So, therefore, this kind of a function is always bounded above by 1, no matter what probability measures mu and nu we choose. Here what can be shown is that the function d turns out to be a metric with the property that as long as mu n's converge to mu in the weak convergence sense, then the corresponding distances goes to 0. Conversely, if the distances go to 0, then the corresponding sequences of measures must converge to mu in the sense of weak convergence. So, this is the idea that weak convergence, there is a equivalent metric which identifies the convergence. So, this metric is usually called the Levy-Prokhorov metric, but however, in more general analysis of weak convergence, there are several other metrics used, which again gives some kind of distances on classes of probability measures. For examples, there are Kolmogorov metric, Wasserstein metric and the total variation metric. However, these metrics will imply the convergence in distribution. So, again if you can establish the convergence through this kind of metrics, then we will immediately have as a consequence the weak convergence of the corresponding measures or the corresponding random variables. So, this Kolmogorov metric, Wasserstein metric and the total variation metric that we have pointed out, this we are not going to discuss in detail. These are just for your information that there are several such metrics which help us look at weak convergence of probability measures as well as random variables. So, in this lecture what we have seen are the proof of Skorohod's representation theorem, followed by certain sufficient conditions for checking weak convergence, and finally, we have pointed out that weak convergence of probability measures and random variables are actually metrizable. We stop here. Thank you.